And so the first talk for the session is going to be Achieving High Performance the Functional Way, and it's going to be presented by Bastian Hagedorn.
Hi, this is Bastian Hagedorn from the University of Münster, and I'll be presenting our functional Perl on achieving high performance the functional way. This one's about expressing high performance program optimizations as rewrite strategies. This is joint work with colleagues from the Universities of Edinburgh and Glasgow. Let me begin with asking the question why we care about high performance in the first place. And the answer is quite simple. We literally cannot afford not to, because apparently it costs about $250,000 to perform state-of-the-art machine learning research. And this high cost is mostly due to the long time required to train neural networks on parallel hardware. It gets worse when you translate the dollars spent into carbon emitted. So here, training this neural network released about 5 tons of carbon into the atmosphere, which is equivalent to driving 11,000 miles with a car. And just to show you how insane that is, here's a map showing a road trip from the north of Norway all the way down to South Africa, which corresponds to roughly 11,000 miles. So clearly, we need to find a way to reduce those costs, and optimizing a program to achieve high performance might allow us to significantly reduce the time required to, for example, train neural networks. So how do we achieve high performance? Here's a naive implementation of a matrix multiplication computation in CUDA, which targets GPUs. And if you know a little bit about CUDA and GPUs, I'd argue that this is quite easy to write and to understand. But unfortunately, this program is also not very fast. So for achieving the highest performance on modern GPUs, this simple program has to be significantly modified. So for example, here's an optimized version of the same computation, which achieves up to 3 orders of magnitude more performance. And if we compare this again to our road trip example and the carbon emitted, 1000x improvement barely allows us to drive 15 minutes on the highway. However, this manual way of achieving high performance requires some expert to sit down for quite some time and to optimize their program in a time-intensive and incredibly error-prone process. So another way to achieve high performance is what I called here the decoupled way, which was pioneered by a domain-specific compiler called Halide. And the key idea here is to decouple what is being computed from how it is optimized. So this allows a domain scientist to focus on implementing the computation, which can then be separately optimized by a performance engineer with a so-called schedule. And this way of achieving high performance is currently very popular, and there are many compilers following this approach. So this particular example here is taken from the TVM machine learning compiler, which is currently the state-of-the-art in generating high-performance machine learning implementation. TVM comes with a tutorial on how to optimize matrix multiplications for CPUs, and we'll take a closer look at that in a moment. So the TVM compiler uses both the algorithm and the schedule to generate an efficient implementation. So here, for example, we see the blocking version from the TVM tutorial, which applies some specific loop transformations. The best version presented in this tutorial is about 200 times faster than the baseline, but only requires to add a few more lines to the schedule. Well, at least that's the idea. So when you take a closer look at this schedule-based approach, you'll find a few problems. So one of the first few things you might find is that the algorithm and the schedule are not fully separated. Here, the schedule uses the same Python identifier that has been declared in the algorithm. And that simply means that both the algorithm and the schedule have to live in the same scope, and that hinders the reuse of the schedule for optimizing a different computation. The next problem is that there is no well-defined semantics for the scheduling primitives. So there is only a documentation online, and for some primitives, this is quite cryptic and basically requires knowledge of how the compiler internally implements the scheduling primitives. And finally, all scheduling primitives are built in, which makes them hard to extend. So typically every primitive like tile or vectorize represents a common optimization you might want to apply, but as soon as you need something slightly different, you're in trouble because there's no easy way to extend the set of exposed optimizations besides digging deep into the implementation of the compiler itself. And this is something we don't often want to do. So this is why with our functional Perl, we aim for a more principled way to describe and apply high-performance program optimizations. And specifically, we aim to separate concerns by expressing a computation at a high abstraction level only without changing them for expressing optimizations. We aim to facilitate reuse by defining optimization strategies clearly separated from the computations. We aim to enable composability by allowing to define both computations and optimizations as compositions of user-defined building blocks. We aim to allow reasoning by giving those building blocks well-defined semantics. And finally, we aim to be explicit and avoid all implicit default behavior of the compiler. And essentially, we argue that a strategy language should be built with the same standards as a language describing the computations. Now, let me show you the functional way of achieving high performance. And our approach follows the same idea of decoupling computations and optimizations, but we're using the well-established functional programming techniques to express both. So on the top left, we have a high-level program that is written in the functional programming language called RISE that is based on an ICFP paper from 2015. And on the right, you see an optimization strategy that describes how to optimize that RISE program. And this is written in Elevate, which is based on ideas already published in the late 90s. Our compiler then rewrites the RISE program based on the optimizations described in the Elevate strategy and eventually generates high-performance code. Our function in Perl is all about how to express the high-performance optimizations, typically applied manually or using the schedule-based approach, however, as composable rewrite strategies instead. All right, let's see how we do this, and we'll start by taking a closer look at Elevate, our language for describing the optimizations. The most basic building block in Elevate is a strategy. And a strategy is simply a function from some program P to what we call a rewrite result. And a rewrite result is simply saying whether the applied strategy succeeded, in which case it contains the rewritten program, or it failed, in which case it contained the strategy which failed. Rewrite rules are examples for very simple strategies, and you could, for example, go ahead and implement the typical MapFusion rule for RISE programs as an Elevate strategy, as you see on the bottom. And this rule simply says that whenever you see a RISE program that contains two consecutive maps, you can fuse those maps and return the fused program. And if there are no consecutive two maps, then this rule is simply not applicable and it fails. For building more powerful strategies, we can combine rewrite rules in Elevate using several different combinators. So for example, the sequence combinator allows to apply two strategies in sequence. The left choice operator expects also two strategies, but only applies the second one in case the first one fails. The try combinator tries to apply the given strategy, and if it is not applicable, it simply returns the unchanged input program by applying the ID strategy. And finally, the repeat strategy allows us to repetitively apply the same strategy until it is no longer applicable. Now, what if we have the following situation? Here you see a RISE program that contains three maps. And if we now want to apply the MapFusion rule we've just defined, there are two possible locations for fusing the maps. So we can either fuse the first two or the last two maps. With Elevate, you can precisely define locations in the AST using so-called traversals. So for example, the body traversal applies a given strategy at the body of a function abstraction node. And in this example, body MapFusion would then fuse the first two maps as you've seen here. Similarly, we define traversals for the other nodes and could, for example, apply body argument MapFusion for fusing the last two maps in this expression. And in the paper, we explain in more detail how to describe precise locations using these and other traversals. Sometimes it's not desirable to specify a precise path, but instead we might want to say something like, apply this given strategy at the first place you'll find. And this is what bottom up or top down do. So these traversal strategies traverse the AST either like from top down or bottom up and apply the given strategy at the first place where it's applicable and then stop. Another useful traversal is the normalize strategy, which applies a given strategy exhaustively until it is no longer applicable anywhere in the given expression. And in the paper, we define a few normal forms for RISE expression. And one simple example of one of those is the beta-eta normal form, which simply applies beta reduction and eta reduction as often as possible. Using those generic building blocks, we then try to implement TVM scheduling language and try to especially define elevate strategies that apply the same optimizations as described in the TVM tutorial, which we've mentioned earlier. So here's what the baseline version looks like. And for TVM, we describe the matrix multiplication using the Python API and use the default schedule to generate unoptimized code. For our function array, we describe the matrix multiplication computation using RISE and its function array primitives like map and reduce. And we define a separate strategy in Elevate, which explain how to optimize this computation. And here we can already see that we have a clear separation between the computation and the optimization. More crucially, TVM's default strategy implicitly describes some way of lowering the program to executable code. And we don't really know how this is performed. With our approach, we aim to completely avoid implicit behavior and describe every transformation explicitly. So here we're simply saying that the dot product should be computed using a single statement by fusing the map and the reduce pattern, similar to how TVM computes the dot product. This way, we implemented each of the 7 differently optimized versions. And in the paper, we describe, for example, how to implement TVM's built-in tile optimization as a composition of only a few rewrite rules and the combinators and traversals we have just seen. Also, our functional approach allows us to define the different optimized versions as reusable strategies. So here, for example, we define the loop perm strategy, which we will reuse in the following more optimized versions. This is the most optimized version implemented in both TVM and our approach. And here you can see that we are able to reuse and to build upon the loop perm strategy, whereas in TVM, we always have to describe the whole optimization from scratch because we cannot easily define our own abstractions. One crucial problem is also that the TVM algorithm has to be changed a few times during the tutorial because the scheduling language is not powerful enough to express all desirable optimizations. Our approach with RISE and Elevate does not require us to do so, and we use the same RISE matrix multiplication that is optimized by 7 different and separate Elevate strategies. To evaluate our approach, we looked at 2 things. So first, in the first experiment, we simply counted the number of successful rewrite steps per versions, which you can see here. And since the baseline version does not perform any interesting transformations, it only requires a few rewrite steps. But as soon as we're performing actual program optimizations, we reach about 45,000 and later up to 62,000 separate rewrite steps. And this shows that our approach is scalable because we were able to define the complex TVM-like optimizations by simply composing a few rewrite rules using Elevate. Also, performing this many steps took less than 2 seconds per version on a regular notebook. So this is no bottleneck. Obviously, we also wanted to see if the performance we achieve with our function array matches the performance achieved by the TVM compiler. And here you see the performance achieved for each of the 7 different versions, and you'll find that we are able to achieve a similar trend, which means that our Elevate strategies encode the same high-performance program optimizations as applied by the state-of-the-art TVM compiler. And if you would like to find out more about a functional way of achieving high performance, simply contact us or have a look at our paper. And with this, I'd like to end the presentation and mention that you can find all our implementations online or in the artifact. Thanks for your attention.
So thank you, Bastian. So for anybody who's wanting to join the authors for the live Q&A, you can click on the link that's in the Slido page for this talk.